At some point, the world was lifeless. It just was a soup of chemicals.
When I was a little kid, I read H.G. Wells and E.E. Smith and Isaac Asimov. It was a great pleasure meeting him and keeping up with him, because how often do you get to meet your gods? I read science fiction more than anything else. I don't read ordinary literature at all. I read some technical things, and I read science fiction novels, and nothing surprises me except why doesn't everybody see that this is the right thing and work on it?
I think simple things like people can produce something more complicated and more worthwhile than themselves.
Well, science fiction is like any field. Most of it's bad, but it's full of a dozen people who I think are the great philosophers of our time.
Imagine that I went back 100 years ago and explained to somebody what I did for a living right now. I couldn't tell them I designed computers because they wouldn't know what a computer was. I couldn't say I made integrated circuits and silicon chips because they wouldn't know what that was.
In science fiction, people say, what if something were actually different? And general literature is, what if things were the same again? It's too boring.
I would have to say, well, what I do is I come up with designs which I etch into stone, magic shapes, which fit together in such a way that the stone can be asked questions. And I can tell it what I want, and it tells me the answers to my questions.
What I'm saying is 1,000 years from now, it'll be 1950 when this animal learned to talk.
It sounds like witchcraft, but in fact, that's exactly what I do for a living.
The stuff before was just emotional utterances, because it couldn't describe processes.
It puts us in a different kind of world.
What does AI mean for us as a species? How have we communicated these ideas over literally thousands of years of history, whether it's Prometheus or whether it's the Golem, looking at all these cultural influences and trying to condense them into one object? That's what you can do as an artist. Oh, you're going to MIT, you have to meet Marvin Minsky and you have to meet Danny Hillis. I found out very quickly that although I was in the mechanical engineering department, the AI lab had a lot better parties. So I ended up having my social circle really be largely from the MIT AI lab. There were parties in Marvin Minsky's house where two people were playing on large grand pianos at the same time improvising.
Well, I like to think of the brain as a cloud of resources. The brain has the order of 400 different pieces of machinery, and if you turned them all on, it would be a great traffic jam. So the emotions are selections from this 400 resources. When you're angry, you turn on 30 or 100 of them. When you're thinking about mathematics, you turn on 100 of them, and some of them overlap and some aren't.
maybe the most important experience I had was meeting Warren McCulloch. And Warren McCulloch was a philosopher and physiologist and great poet. I think maybe 100 years from now he will be seen as one of the great philosophers of the 20th century.
Will we one day in the distant future perhaps even create beings superior to ourselves? Beings who will survive us on this planet? Dr. McCulloch thinks it possible.
Somehow the purpose that a machine, no matter how complicated and how clever, could have, to my mind, isn't equatable. When man has gone, these machines would in essence be purposeless.
I doubt that. I would say in essence they would be purposeful.
And there would be, in your feeling, nothing gone and nothing missing from the world.
Well, you mean in the sense in which the dinosaurs are missing?
No, I mean in the sense of something important.
Well, aren't they important? Weren't they important?
Do you think we'll make a machine to equal the brain, the human mind?
As far as arithmetic is concerned, they're already way ahead of us.
I mean in general, memory, idea formation, a soul, so to speak. You know, when first the machines came out, everybody thought that they did in fact.
I'm sorry, let's leave the soul out.
All right. Well, do you think that the computer will approximate the human mind in all respects?
Computing machines think with a language which is number. Everything else we transfer into number to make them work. Okay? They are lousy when it comes to perception. They don't have any underlying natural language the way we do, that we share with the animals. And when you want to make them spot objects, develop a model of the world around them, you find out they're not the right device. Okay? If you want them to play chess, all right. Our chess playing program at MIT is already a #2 chess player. In another year, I think it'll be a #1. It will not be a master at the end of another year. But it's 6 years old. But in 6 years, it's all, from nothing, it's come up to being a #1. No human being ever did that. So I expect them to go well ahead on these kind of problems, because we can reduce these things to number.
But they'll never be able to write a piece of poetry like Warren McCulloch can.
Why not? Not with our loneliness, not with our dream, can earth be taken and our heaven won, but with our toil and ponderous reasoning, and with our little changing of the cosmic stream. Sing then to the men that make the road, and tunnels through the hills and bridges slung, over the wide valley and the deep ravine, till streets are crowded with the whirling cars, and the long leveled track rumbles to the train. Sing to the men that left some safe abode, and gazing fixedly on distant stars, conquered the sea's tumultuous domain. With oar and sail and steam, gallant they clung to their wide quest over unfathomed green, bearing the timorous body and the heart's load, till now through space the wireless word is flung, and the skilled pilot guides the soaring plane. With these we win the world, to these my ode.
And even today, which is 40 years later, sometimes when I'm stuck writing something, for example, I could hear his voice.
I'd read a science fiction book called Have Spacesuit Will Travel by Heinlein. And in that story, the kid wins a spacesuit in the lottery and gets to go to space, and he ends up saving the world and getting the girl, and as a prize for him saving the world, they give him a scholarship to MIT. And I didn't know what MIT was, but I decided that's where I wanted to go. In The Wizard of Oz, all starts out in black and white, but when she opens the door in the Land of Oz, everything turns into Technicolor. That's what MIT was like for me. I saw this whole other dimension to the world. I met all of these people who knew about everything and who were excited about ideas. And the whole world kind of opened up for me.
It needs a good teacher. The teacher comes up to the machine, which contains a vision system for describing things, and I give it an example, for example that, and say, this is an arch. Well, the machine describes it, and the description, the structure that the machine builds up inside its memory is something like this. There are 3 objects found by the vision system. They're all identified as blocks, and it notices certain relations between these objects. For example, that this one supports that, and this one supports that.
What I was really trying to do was meet Marvin Minsky, but every time I would go by his office, he wasn't there. And I started asking where Marvin Minsky was, and they said, oh, he comes in at night and he works down in the basement on this computer that he's building. So I used my key and I came in at night and I went down, and sure enough, there was Marvin sitting there working with some of his students. But I was too awed by Marvin to actually go up and talk to him. So I just hung around and I looked at the diagrams of the computer that he was building, trying to see if I could come up with something clever to say to him. And I noticed that there was actually a bug. There was a design error. And so I thought, oh great, this is my entree to... So I went up to Marvin and I said, excuse me, but I think there's a mistake here. And I pointed out to him, he said, yes, fix it. So I fixed it on the diagram. I said, it needs to be rewired. He said, well, rewire the computer, you know. And so I changed the design of the computer, and then I found another one, and then after a while I stopped asking him. I would just start changing the diagrams and redesigning this computer and rewiring it. And after a while, Marvin just assumed that I worked for him. And so that's how I met Marvin Minsky. And then we would work late at night and there wouldn't be anything to eat, so he'd invite me over to his house. And that's how I met his daughter also. And his daughter became my girlfriend after a while. And I eventually just moved into his house. Then we cleared out the basement. And I lived in Marvin's basement while I worked with Marvin on this computer. So by the time I got to MIT, people had sort of given up a bit on this neural intelligence. And they were working mostly on the symbolic intelligence. And the symbolic intelligence is kind of what it feels like to think, because it's the part of intelligence that's very visible to us. And so just as I was arriving at the AI lab, people were beginning to understand that intelligence was kind of more complicated. And Marvin kind of led that effort. And he started thinking of intelligence as a kind of society of little intelligences that interoperated with each other.
Marvin was writing The Society of Mind at that point. It came out, I believe, in '83, which is when Danny started thinking machines. Of course, Danny, as Marvin's PhD student and protege, the Society of Mind was what at least Marvin's students we're talking about and thinking about. In our corner of the AI universe, that's how people thought of it. And when the book came out, I did get a copy of the book, and I'm going through, and it's like, oh yeah, this is everything that Marvin's been talking about.
What is life? One dissects a body, but finds no life inside. What is mind? One dissects a brain, but finds no mind therein.
When I was a graduate student, I was very interested in making a thinking machine, an artificial intelligence.
How could solid-seeming brains support such ghostly things as thoughts? This question troubled many thinkers of the past.
There have always been kind of two schools of thought in artificial intelligence. One of them is kind of the emergent intelligent idea. The idea that you'd have some system that was a fundamentally simple system of replicated parts that had in it the inherent ability to organize. So neural networks are the perfect example of that.
To explain the mind, we have to show how minds are built from mindless stuff, from parts that are much smaller and simpler than anything we'd consider smart.
And so that idea was a very early idea in artificial intelligence. And in fact, Marvin worked first on that idea. And he built little electronic neurons out of tubes. The problem with that idea was that it really needed a lot of neurons. And so you had to get up to very, very large numbers before you got that kind of emergence. They definitely had notions of how to do this. They, in practice, couldn't do it very much.
Our first intuitions about computers came from experiences with machines of the 1940s, which contained only thousands of parts. But a human brain contains billions of cells, each complicated by itself and connected to many thousands of others.
I knew that the computers that we had available at the time were not nearly powerful enough to do it. So I had to make a computer that was thousands of times more powerful. So part of why I built the connection machine was to try to get the number of neurons up. And so that's why I started making parallel computers, was to make a thinking machine with them. MIT being what it was, even though I was an undergraduate at first when I started working on this, and eventually a graduate student, I would go to Jerry Sussman or Marvin Minsky or something and say, I want to hire your op student. I would get these great MIT students like Brewster Kahle, for example.
I started working with Danny at MIT early on this project when he was a 24-year-old graduate student. And
How old were you?
I was 20. And I wanted to build the Library of Alexandria version 2. I wanted to build the global brain. And Danny had this idea on how to make a machine that would be fantastic. And I said, oh, how hard could that be? I'm in the very last part of this 60s utopian generation. He wanted to build a machine that would be proud of him, which I thought was really an interesting way of viewing the whole thing.
We just had the ability to start making chips ourselves. I figured out you could actually make like 64 very simple computers on a single chip.
Parallel processing at that time meant 2 processors, both very powerful, maybe 4. And above that, it's just too complicated. You can't do it.
So I started designing chips like that and imagining big arrays of these that you could have 1 million of these, was my initial thought. Later I scaled it back down to 64,000 out of practicality. But the original idea was you could have 1 million computers and they would all have the ability to talk with each other, and you could use them like neurons, and you could use the kind of McCulloch-Pitts learning algorithms.
I was an undergraduate at MIT. I could design chips. I mean, what the heck?
The project started getting more and more expensive, and it became a little bit ridiculous having a student have all these people working for him and spending millions of dollars. And so eventually I realized I had to start a company on the outside to do it. So that's how Thinking Machines got started.
Especially then in the early 80s, it was unusual for a doctoral candidate to start a startup company and actually get millions of dollars to carry out the idea. But because he was a protege of Marvin Minsky and MIT has kind of good connections,
ultra-fast computers so powerful, it's revolutionizing work in laboratories and businesses.
Really, it's a 24-year-old Danny's kind of wacko dream. Yes, there's Marvin Minsky, who seemed more establishment, or at least older, but it was still kind of wacko. And let's give this thing a shot.
It turned into the largest employer in Cambridge, actually. It had about 750, 800 people.
Many scientists thought such computers couldn't be built for decades, but as David Barron reports, the advanced technology is proving itself today.
These are the heady days of AI and computers when we could see the future.
You know, he had, I think, 150,000 square feet of prime office space around Kendall Square.
Hillis's multi-million-dollar machines and those built by a handful of competitors are based on a technology called massive parallelism.
How do you go and make a company out of a bunch of bonzos from MIT and make that come about and communicate?
Danny Hillis is a legend in the world of computing.
It really turned into a company, which was not really what I had intended exactly. I hadn't really thought that part out so much. I just wanted the machine.
What a fantastic trip.
Really, the first thing I heard about this was about 3 days after the graduation ceremonies, where I got my master's in mechanical engineering from MIT. Danny said, "Hey, I'm starting this company to build my doctoral thesis. We don't even know, however, if it's physically possible to build the machine as we're envisioning it. Can you come and work with us?" And he literally did, with a twinkle in his eyes, say, "And if you do come, you get to work with Nobel physicist Richard Feynman." And that sealed it for me. I said, "Okay, where do I sign? Where do I sign?"
Richard first heard about the connection machine. He said, "That's a kooky idea." And of course, for Richard, that meant he was interested in the idea. And so he started asking questions about it. And a lot of times he was interested in it. I guess he wasn't so much worried about whether it was a real idea or not, but more was it a way of generating new ideas. And then by the end of the conversation, he said, "Oh, and by the way, do you want anybody to come there for a summer job?"
you know, he was still teaching physics at Caltech, but he spent his summers hanging out with us at Thinking Machines.
And the problem that Feynman worked on was how you get these chips to talk to one another. And in fact, Richard did some analysis that said that we could build it in a little bit simpler way. But initially we didn't trust his analysis because it was based on these sort of crazy physics ideas. It was a very unconventional way to look at a computer. So we didn't quite trust his analysis, which suggested that we could in fact have fewer circuits on each chip. But then in the end, we couldn't quite fabricate as many circuits on the chip as we wanted to. And so we decided to trust Richard, and we indeed produced the smaller number of circuits. So he was right.
First off, I've asked the electrical engineers, what do your boards look like? What are the cabling requirements? And they said, well, we've got these 2 feet by 2 feet board and they have to have connections going off on all 4 sides. And I said, okay, how many of these boards do you need? 128? Okay, that's going to be kind of a big machine. Everyone was talking about, well, it's got to be hooked together in a 12-dimensional boolean hypercube structure. And I go to Danny and said, what is a boolean hypercube? And he said, oh, go ask Richard. So I went to Richard Feynman. He just said, oh, that's easy, and then reached for paper and pencil and started drawing diagrams. This is classic Feynman. A one-dimensional cube can be thought of as a connection between a single processor and another processor. You take that structure and you double it and you connect the edges. Then you have each processor connected to 2. You double that, you connect the edges. You've got a cube where the corners of the cube are processors. And then you double that cube, and then he drew a cube inside of a cube, connected the edges, very easy to draw, and said, here's a 4-dimensional cube. And after that, it becomes too hard to draw. And I'm going like, right. And I have to draw a 12-dimensional cube, and I have to give wiring specifications where I tell the engineers how each of these processors is connected to 12 other processors. Feynman gave me a cube within a cube, and I'm playing around with it topologically, and finally I take the inside cube, put it next to the outside cube, and say, okay, the connections are like rubber bands, they're movable. And I said, okay, so what do? We take that, we duplicate it, we connect the edges. Oh my God, it looks like a 2-dimensional cube, that is to say a square. But each corner is not a processor, it's a cube of processors. Well, let's duplicate that, connect the edges, we've got a cube of cubes. And oh my God, every 3 dimensions, that cube structure replicates, and a 12-dimensional cube is simply a hypercube, whose corners are 9-dimensional cubes, whose corners are 6-dimensional cubes, whose corners are 3-dimensional cubes, whose corners are processors. It's easy. At that point, I said, you know, we can actually make this look like any other machine out there. It can look like a refrigerator, you know, or like a heating element. Then the question arose, okay, what do we need out of the form of the machine?
And so we really thought of it in that kind of heady way, as there was a generation change happening.
A generation change in the machines or in the people? And what year was this?
In species. I mean, we were bringing up the next generation of evolution.
Of Homo sapiens?
Well, Homo sapiens will be about as relevant as zoo animals.
And remember, like I said, Danny and I are about the same age. We were then 25 or 26. The other engineers, like Brewster Kahle was even younger. Carl Feynman, Richard Feynman's son, who worked at Thinking Machines, was even younger. So we're all in our mid-low 20s, and we're competing against the big boys of supercomputing who are, you know, at least in their 40s or 50s or 60s. We were going like, oh, these kids, you know. And we wanted to bring in customers and tell them, this is a completely new paradigm for supercomputing. You've never seen a machine like this before in your life.
If we're going to bring up our new overlords. Let's have them read good books. Kind of as Aristotle taught Alexander.
What if they come in and say, oh, I just bought a new refrigerator, it looks exactly like that. Why would I pay $3 to $5 million for something that looks like my refrigerator? Let's talk about materials and about color and how do we make the machine come alive? For many people, computers are bloodless beige boxes with incomprehensible electronic displays that never work anyway. Scientists involved in computer research, on the other hand, see computers as the tools for building new worlds. They see themselves as pioneers and settlers in a wilderness conquered not by the plow and the rifle, but by mathematics and programs, by the brain and by abstract thought. We at Thinking Machines were all members of this electronic tribe. In the design of the connection machine, we wanted to express the mystery of the world of computers in a way that would capture the imagination of all who saw it. The company said, listen, in the $3 to $5 million machine, the packaging is going to be such a tiny fraction of the cost. Just make it look fantastic. The inspiration for the design, I believed, should come from the ideas of the computer scientists who were developing the CM2. They talked of the machine as a cerebral starship, a vehicle that could open up boundless new frontiers, or as an immensely complex, constantly fluctuating electronic society. Their visions of the machine evoked in my mind the sculptures of the Italian artist Arnaldo Pomodoro. His simple, smoothly polished geometric forms have always suggested strange planets or massive starships to me. Beneath the smooth and the serrated surfaces of his sculptures, there seemed to be room for entire worlds, high-technology cultures, long-dead civilizations. His work communicated a sense of immense, seething complexity beneath the surface of a geometric, man-made object. These were the feelings and images I wanted to capture in the physical form of the CM2. Danny said, the machine should not be taller than you. If it's around your height, then it's not an overlord that has come here to dominate you. It's a member of the family. And he really used that term, that this machine should be a member of the family. It should be something that we work with, that's part of our life, that's part of our story, that's part of what we want to do in the world. Our desire to find a form for the machine that expressed its significance in the development of computer technology led us to re-examine the basic tenets of 20th century design philosophy. The basis of this philosophy for almost a century has been form follows function. A mechanical device expresses its function in the visible world. It is graspable and moves or physically affects its operators and their world. We, however, were working with a very different sort of product. Electronic machines are incomprehensible. They do not visually explain themselves. If you look into the insides of a machine, any machine, including the connection machine, it looks the same. You've got lots of cables, you've got lots of boards, you've got lots of chips and transistors and whatnot. Making the innards of the machine visible from the outside would not tell you anything new about the machine. It wouldn't tell you anything about the machine. It could be something that just, runs the heating for your building, for that matter. It became clear to me that we had to extend the meaning of function beyond physical structure, beyond the purely mechanical, into the abstract. Indeed, for people who work with computers, the image of the machine in their minds has nothing to do with boards and cables. To truly understand the function of a computer, one has to look at the schematic representations that computer scientists use to talk about the architecture of a computer. The structure buried in microscopic layers of silicon and hidden in mazes of electronic circuitry. In a symbolic processing machine where the function is invisible, the function has to be conveyed symbolically. Carl Feynman had described a fantasy of the CM1 as a vast cloud of lights that flickered as they sent their electronic messages back and forth, like the firings of neurons in a brain. The connection machine was this cloud of red blinking lights, and they were blinking to communicate with each other. It is a hard geometric object, black, the non-color of sheer static mass. But it is filled with a soft, constantly changing cloud of lights, red, the color of life and energy. And the lights are literally the status lights, one for each processor chip, but we move them forward at the edge of the board so that they could be visible through these translucent doors. Carl Sims programmed them to say, "I blink, therefore I am." This would be a way to ornament without decorating, to express a symbolic aspect of the machine using raw form, size, proportion, color, and material. We in the industrial and post-industrial cultures have lost the tradition of ornament as an important carrier of symbolic meaning. We must relearn how to invest designed objects with a symbolic significance that can speak to the experience of living at the beginning of the third millennium. That first impression had to astonish, delight, and convey the information about how that machine was really a completely new paradigm, a form that you've never before seen in your life. But you've always intuitively felt, yes, that's what an artificial intelligence would look like, an artificial brain would look like. And it made them a lot more willing to write those checks, let me tell you. You can call that a marketing ploy, but I think it's much more than that. You know, you don't pay $3 to $5 million for something that someone else tells you is probably good for you. You do it because you personally think, yes, this machine is going to be worth it, and I am ready to go in front of, legions of doubters and convince them that this machine really is worth it. What I call the technological sublime. Some sense, some emotional sense that this mysterious object will transport me and my capabilities into a future where I can do more with it than without it.
The things that are going to go to the stars, they're likely to be more relating to connection machines than they are going to be relating to human biology.